Okay, so what did we learn? So in chapter 4, so we will learn about the hardware architecture, of RISC-V processor, right? So actually until the chapter 2, so we learned about the instruction set architecture. And then, so the instructions are the part of software. And then the instructions just define the behavior of hardware. And then in chapter 4, so we will learn how to implement the processor hardware. So the processors execute instructions. So which means the processors generate the result of instructions, right? And then we will learn how to design. And then so also in chapter 4, you need to focus on how the performance issues. Okay, so in this model, so actually I mentioned that the instruction set architecture does not consider about the timing, of instructions. So which means actually in a software view, the software think that the instructions are atomically executed. So atomically means that the instructions are separately executed, and then the following instruction can be executed just after the completion of previous instructions. Okay. That means atomic execution. But in reality, so actually, in order to increase the performance in the real hardware, we cannot implement the processor architecture like this. We cannot, okay? So actually, when we design a processor hardware, we need to focus on delay, the delay of instructions. It's a delta T, okay? So we need to consider the timing delay of the instruction. And then, so so this delay determines the performance of our computer system. So in chapter 4, we will also focus on the performance issues of hardware architecture. Okay. And then so I so in the previous class I explained about the required steps for executing instructions. Okay. And then I I categorized the required steps as the 5 steps. So instruction fetch, instruction decoding, execution or memory access, and write back. Okay. So these operations, so these steps are required. Okay. So required means that when we design our hardware, then we need to design hardware components that perform these required operations. Okay. So it's just the implementation. So like the software implementation, so we can just implement the hardware components that perform these required operations. Okay. So in chapter 4, so we will also learn about this hardware design. So hardware design of the components in the processors, in a processor. So, okay, so in the previous class, we learned about the logic design conventions. Okay, and then so you need to actually in the following labs, so you will be you will be requested to design processors using system Verilog. That's why I explained about the logic design conventions. Also, I posted some system Verilog lectures on the Piazza. So if you did not take the logic design course, so this is the logic design course, then you can watch the videos. Also, you can read the lecture slides, okay, on the Piazza. Okay, so and then but you need to understand how to. So this is a very important topic. So methodology. So you need to understand how clock period is determined in a digital design, right? So why clock period is important or critical? But it is because no execution equation, the instruction count, CPI, and then TC. So you can find that the TC, the clock period, so actually the execution time is proportional to the clock period of the system. So in order to increase the performance, so we need to reduce the clock period, right? So that's why, so this clock methodology, so that's why it is critical. It is very important to understand how clock period is determined, okay? And then, so that's what I explained, but so you can just understand the digital design, the digital logic design like this. So you can find the D flip-flop here and D flip-flop here, and then D flip-flops are synchronized with the clock signals. And then between D flip-flops, you can find this combinational logic. And then this clock period of this clock signal, it needs to be greater than the slowest delay of that is combinational logic. Okay, so it means, and then this slowest path or slowest delay is called the critical delay or critical path in the this combinational logic. So this, because this the delay of the combinational logic determines the clock period. So we need to reduce this delay, the critical delay of this combinational logic, right? So you need to understand that this. And then, so I just showed some examples of deep flip-flop implementation in system Verilog, okay? And then we need to avoid latch, okay? It's a bug. Okay, so now I will explain how to combine these digital logic components to implement the processor hardware. Okay, so just remember that. So the required steps, the 5 required steps for executing instructions. Okay, 5 steps are instruction fetch, and then instruction decoding. So instruction decoding includes the real decoding plus register read and execution, and then memory access, and then write back. So it's a write back to register file. So it's a write to register file. So then let's see let's see how to implement these operations. Okay, so what is the required operations for the instruction fetch? So what is required? So firstly, we need to update the program counter. Okay, so usually the program counter is the program counter plus 4, right? For the normal instructions, not branch instructions. So usually the program counter of the RISC-V instruction is incremented by 4, right? It is the size of instruction is 4. And then using the PC, then we need to access the memory, right? And then I mentioned that the PC is the address of instruction. So which means in order to read instructions from memory, then we need to access the memory using the PC. Okay, so what is the memory? Address is given, then the data in this memory space indexed by this address will be read out, right? So this is the memory. So we can implement this instruction fetch operation like this. So you can find the program counter here. And then, so actually this is the register, okay? And then we can implement the register using D flip-flop, right? So if you took the digital logic design course, so you can, I believe you can remember that a register is a group of D flip-flops, right? And then we can store temporary data in this register, okay? So PC, so you know, in a RISC-V processor, so we are learning about the 32-bit computer system. So the width of this PC is the 32-bit. Okay, so which means that the PC register includes 32 D flip-flops, right? So because the register is the group of D flip-flops. So actually this PC is synchronized with the clock signal. Okay. So and then you can find that the output of this D flip-flop is this line, right? And then using the PC value, then you can find that the memory is accessed. So you can find that PC, the output of this PC register is connected to the address input. Okay, this is the input. Address input of the instruction memory. Then we can read instruction. So this is the output of the instruction memory, but the address is given to the instruction memory. Then we can read the instruction. The instruction will be read out from this instruction memory. But so why? So you can just see that why is instruction memory not memory? Okay. So it is because in a processor design that we can separate. We need to separate the instruction memory and data memory. So this is the performance issue. Okay, so you can so this design, so just to remember that, so we can separate the instruction memory and data memory here. But anyway, the instructions are here. So instructions are stored in this instruction memory, and if the PC is given, then we can read the instruction. Also, you can find the this adder, and then so PC is given to the one of input of this adder, and then the another input is 4. So what does that mean? This line represents the PC plus 4, and then PC plus 4 is feedback to the PC register. Okay, so you can find that usually the PC is updated by PC plus 4. Okay, so this is the instruction fetch operation. And then, so in this hardware design, so you can find some components like the program counter register and then instruction memory. And then you can also find the input and output ports. Okay, input and output ports of these hardware components. So, and then we can just connect these port, the output port of a certain component to the input port of another component. So which means the data is transferred, these digital signals or data are transferred from one component to another component. Okay, so we can design this digital system, right, processor hardware like this. Okay, Just to remember. So we can just design a certain component, and then we can just connect these components. Okay. So this is the instruction fetch operation. And then so now the instruction decoding. So for instruction decoding, the processor needs to read operands from general purpose registers, and then also you can find the registers here. Okay, so you can find that these are registers, and then actually, so there are multiple general purpose registers here. So this component is called the register file. So usually I use the RF. So it's a register file. So it means a group of general purpose registers. So instruction, we can read an instruction from the instruction memory, and then so we need to read the operands from registers. How? So for example, add x1, x2, x3. So we can use the register number here. So at x2 and x3. So using the register number, the source register number is given to the register file. Then we can also read the data in these registers, right? So register is also very small memory. So which means that we can read a certain data, we can define a certain data like this is the register array, and then the index. The index is the register number. So you can find that, oh, register number is a given. Okay. And then also add instruction include. So this is the R type instruction, right? The R type instructions include three register numbers, right? The two source register numbers, and then one destination register number, right? So in order to write a data, also you need to access the general purpose register using the destination register number. So you can find that the three register numbers are given to this register file. So this is the instruction decoding. So actually instruction decoding during the instruction decoding, a processor just reads operands from register file. So you can find that two source register numbers are given to register file. Then we can read the RS1 data and RS2 data. So you can just understand the register file like the also memory. Okay, so so register is the array. So it's an array, and then if so it is the array data, and then if the index is given, then we can read the data in this the array. Okay. So this is the instruction decoding. So, but actually, a processor needs to include the decoder. Okay. So in chapter 2, we learned how to encode. Encoding means that the assembly instruction is translated into the machine instruction. And then in order to understand, in order to figure out the instructions, the type of instructions or operands in an instruction, then a processor needs to decode. Okay, so decode means it's a kind of analysis. Okay, so actually So the process also needs to include the decoder, but decoder is not shown in this figure. Okay. So anyway, the register number is given, and then we can read the register data, register operands from this register file, right? RS1 and RS2 is given. And we need to perform add operation, right? Or some other operations, okay? So sometimes we can perform the processor needs to perform addition, subtraction, multiplication by the some instruction type. So in order to support the various arithmetic operations or logical operations, we can use the ALU. So ALU is represent the arithmetic logic units. Okay, so we can ALU can perform addition, subtraction, this is arithmetic operations. Also, ALU can perform logical operations such as AND or exclusive or the ALU can also perform the shift operations. Okay, so these arithmetic or shift or some logical operations are performed by ALU. Okay, and then based on the instruction type, then we can generate the of the result like the so if the instruction is add x1 x2 x3, then we can calculate the x2 plus x3. So this is the result of addition. Okay, and then this in this result so this is the execution. Okay, and then this result needs to be stored in the register file, okay, using the destination register number. So in order to update the general purpose register file, so we need to also provide the destination register number and result, the result of ALU. Okay, so this is the write back. Okay, write back operation. But so I just explained about the arithmetic instruction like add instruction, but memory instruction like load word, x1, offset, and immediate offset, and then x2. So we can also use, so processor can also execute load instructions or store instructions. So those are memory instructions. So processors also need to perform memory accesses. Okay, so you can also find the data memory here. Okay, so but what is required for this load instruction, load word? So firstly, we need to perform x2 plus immediate, right? So this is the add operation. And then using this address, so generated address, we need to access the data memory. And then we can get the, the request data from the data memory. And then this red data is updated to the destination register. So return to the destination register. This is the load instruction. So memory operation is also required. Okay. But in order to access the memory, the processor needs to perform X plus immediate. So source register 1 plus immediate, right? So this operation also can be done by ALU because ALU can perform addition. Also, you can find that another path is here. So it means the immediate value, because the immediate data is included. Immediate data is just included in the instruction, right? So you can find that instruction is connected to the one of input of ALU. Okay. So address is generated, and then this using this address, then we can access the data memory, and then data is read out. And then this data also can be written back to the register file. Okay. So this is the memory operation also. And then I already explained about the write back. Okay. So in this figure, in this slide, and so in this figure, I just explain which operations are required for executing instructions. So, and then we can design some separate hardware components like the instruction memory and register file, ALU, and then data memory. And then these hardware components include input and output ports, right? So which means the input is given, then the output, the designed outputs are generated. Okay. And then in order to implement these required operations, I just connect the input and output ports of these hardware components, right? So we can design the hardware like this. Okay. So we can design some black box. So this is the black box, the hardware components, and then but we can just define the input and output. That means the function of the hardware components, and then we can just connect the input and output ports of these hardware components to build the larger block, the larger hardware blocks. Okay. So this is, so you can just find that okay, so we can just connect the input and output of these black boxes. Okay. But actually this is not, this cannot be implemented by hardware. So so you can find that okay, so you can find that this is the PC plus 4, and then even though I did not explain about this adder, but this adder is required for the branch instruction. Okay, and then this is the target of branch. So this is because sometimes the PC, if the branch instruction is executed, then PC can be updated by PC plus 4 if the condition is false. And but also the PC can be the target of the branch instruction. So actually the target of the target plus PC, okay, because that's why we are using the adder here. So it means that the condition is true. So what does that mean? So sometimes the PC, the program counter can be PC plus 4, or the program counter can be the target of a branch instruction, like the PC of the branch instruction plus target, the immediate value. There are two different cases. And then in this figure, because there are two different cases, like PC plus 4 and the branch, and then we just connect the wire like here. But in hardware, it is not possible. So it is because if we just connect the two wires like this, so it means if wires are connected, these wires have the same value. Okay, so actually the same voltage level, right? Because so so actually the digital hardware the figure out the data value using the voltage level. So wires are connected, then these wires have the same voltage levels. Okay, which means the same values. But we intended that, oh, this wire is the PC plus 4, and then this wire is the target of the branch instruction. So actually it's different. So how can we handle this? We need to use the multiplexer. So okay, so where is multiplexer is not here. So what is the multiplexer? So you can find that the multiplexer here, right? So multiplexer, so this is the functional behavior, the functional operation of the multiplexer. So you can, so this is if the S is 1, then I1 is selected to the output. If the S is 0, then I0 is selected. So based on this S value, then I0 can be connected or I1 can be connected to output Y. This is the behavior of multiplexer. So we can implement this one. So I mentioned that, oh, based on the condition of the branch instruction, then this is the PC, the next PC actually. The PC can be PC plus 4, or this PC can be the target. Target means the PC plus immediate of branch instruction. Okay. So based on the condition of the branch, then PC can have two possible values, and then we can select the one PC value from these two possible values. So this operation is multiplexer, right? So actually, we need to implement this part, like the multiplexer, and then this one is connected to the one of input of a multiplexer like I0, and then this one is connected to the I1, and then using the selection signal, we need to select the output of this multiplexer. Okay, you have to understand. So in this figure, so in this slide, I just connect the, oh, this is the input and this is the output, and then which data is required, which signal is required. So we just connect it. But actually, it's not possible. So if for this case, we need to use the multiplexer. And then in order to use the multiplexer, then we also need to figure out. So we need to figure out this S value, the select value. Okay, so I will explain later about this select value. Also, you can find this one is also the same situation. So one of the input is this is the result of ALU. So this is the output of data memory. And then actually the result of ALU is required for all type instructions, right? And then the output of main memory is required for the load instruction. Okay, because and then this data is returned back to the register file. So we can select one of signals, one of data. So we need to use the multiplex here. Okay, so one of the data can be the output of ALU, and then one of the data can be the output of data memory. And then this part is the same. Sometimes so with this ALU, we can calculate the RS1 or RS2 for add instruction, or we can calculate the RS1 plus immediate. Okay, so RS2 data can have two possible cases. So it's like RS2 and immediate. So in this case, we also need to use the multiplexer here. Okay, so based on the steps for executing instruction, then we can just build the hardware by connecting the input and output ports of the hardware components. And then for these cases, we need to use multiplexer. Okay. Okay, so this is the first step, the initial step for designing a processor hardware. Okay. Okay. Now let's focus on the each component, each hardware component. Okay, so you can find the building or data path. So then what is a data path? So you can find the terminology data path. So data path means that elements. So it's a hardware element or hardware components that process data and address. Okay. So which means, a certain data is given. So this data path element receives a certain data or address, and then it also generates another data. So based on the function of this data path element. So we can define the function here. So for example, this is if so let's think about the instruction memory. So memory, then this instruction memory receives address data as an input, right? So this is the input. Input is the address, and then the output is the instruction, right? So, so this is our data path. It is because it received the input data like address data, and then it generated also output data. Okay, so instruction, and then we can define the function of this instruction memory. How? What is the function? The function is instruction is the, so if the memory, and then the array is indexed by address. Okay, so this is the function. So this is the function of this instruction memory. Okay, so you can just understand the data path. A data path is the hardware component or hardware blocks. Okay, and then these hardware blocks received some signals or data, and then it also generates the output data based on the function of these hardware components or hardware block. And then in reality, and also another component of this hardware is the delta T. It's a delay. So what does that mean? So the output will be generated based on the function of this hardware component, okay? But after delay. So actually in delta T, okay? So you can understand the hardware components like this. Okay, input is given, the output will be generated and based on the function, defined function, but after delay in delta t. Okay, so we can build each data path. We can design each data path using the the HDL. Okay, actually this is the the so you will be requested to design actually each data path element using system Verilog. Okay. Okay. So okay, let's see the instruction fetch step. So I already explained. So this is the basic function, the basic operation of instruction fetch. So what is required? We require the 32-bit PC register. Okay, so so you can find the clock input here. So it is synchronized with the clock signal. And then so this is the PC. So which means that the input of this PC register is the next PC. So it is the PC underbar next. And then this is the PC, the current PC. Okay. And then, the current PC is given to the instruction memory. Then we can get the instruction. The size of an instruction is also 32-bit. Okay. Because so we are learning about the 32-bit RISC-V instruction set. And then this PC, so this is the PC, the core, because this output is just connected to this line, this wire, and then you can find the 4 here. So what is this output? Obviously, PC on the core plus 4. Okay. Then how can we implement this operation in system Verilog? So I already explained the operation of this program counter register. And then I explained that the program counter is a register. Actually, a register is the group of D flip-flop, right? Okay. So we can implement the PC register like this. So this is the 32-bit register, right? So we can define the 32-bit register signal PC underbar core like this. Okay. So you can find the logic data type in system Verilog. Okay. So it defines the data type. Okay. The logic data type, and then logic data type can have 1, 0, and then high Z, and then don't care some values. Okay. And so anyway, you can just understand that this is some signals in the hardware. Okay, we can define the PC underbar core. Okay, so in the previous figures, I just defined this is the PC underbar core, right? The output of the PC register. Then what is the behavior? What is the behavior of this PC underbar core? So you can find that we need to use the arrays underbar FF. So it means that it will generate the flip-flops. Okay, FF represent the flip-flops. And then in order to generate the flip-flops in system Verilog, then we need to use the arrays underbar FF. And then it is synchronized with the clock signal, right? So synchronized with the positive edge of clock signal, and then it can be controlled by reset signal. And then, so reset signal is required for stable operation of digital system. So, and then this is the negative reset. So you can find that the reset signal name is the underbar B. So it includes the underbar B. And then usually it represents this is the negative signal. So negative signal means that this signal is activated if the signal value is 0. So which means that reset underbar B represent it make the signal reset. It makes the signal reset if the this RST underbar B signal is 0. So this is the negative signal. Okay. So it is because usually we assume that if the signal is 1, then it is the activation, and then 0 is the deactivation. But negative means that it's opposite. If the signal value is 0, this means activated, or signal value is 1, it means deactivated. And then in this example, the reset is the negative reset signal. Okay, which means if this signal is 0, then it is activated. So it makes system reset. Then usually we use the negative reset. This is the system. So what is the output of PC underbar core? If the reset underbar B is 0, right? You can find the not signal here. So which means if the reset underbar B is 0, then PC underbar core becomes the all zeros. And S begin, then what is the normal operation? What is the normal operation of this PC underbar core? This is the piece. You can find that this is the PC underbar core, right? Current PC, and then it's a 4. So what is the result of this adder? This is the PC underbar core plus 4. Okay, and then you can find that this PC underbar core plus 4 is given to the input of PC register. So this is the normal operation. Okay, so for the normal case, so I just ignore the branch case in this example. So if the reset is 1, okay, so normal operation, PC underbar core is the PC underbar core plus 4, right? So we can implement the program counter register like this. But you need to remember that. So I just ignored the branch case here, right? So this is the behavior model. Okay, so we just define the behavior of the data path element, right? And then we can design the data path element like in system verilog like this. Okay. Then how about the memory? So I just I already explained. The address is given. Then the output is the instruction. Okay, you can I just name this is the D out. So it means the data out. And then this is the instruction memory. And then this instruction memory has the data array. Okay, this is the array. This is the data array. So you can find the data array in IMEM. IMEM represents the instruction memory. And then I define the data. So a size of a single data element is the 32-bit, right? So it represents the size of a single data array. Okay, so this is the name of the array. And then how many elements? There are 256 elements. Okay, so which means that it declares the array data like data 0 to data 255. Okay, and then each element of this data includes the 32-bit data. So so you can find this declaration here. So it defines the size of a single element, and then this one defines the number of elements, in this array. Then what is the D out? So address is given, and then the D out is the instruction. What is the D out? So data array is indexed by which value? Indexed by input, right? But I mentioned that the most CPU use byte address. So what is the byte address? The 1 byte occupies address 1. And then in the instruction memory, so each instruction is 4 byte. So this is the address, but we need to use the address actually divided by 4, right? Do you understand? Because this address is the byte address, and then I just define the size of a single data element. The data array element is the 32-bit. It's a 4 byte. So in order to access each data element, then we need to use the index value, but the index value is the input address divided by 4, right? To understand? Because the size of this data array is 32-bit, it's a 4 byte. But actually, in the hardware, divided by 4 is just the right shift by 2, or we can just remove the LSB 2 bits, right? Okay. Okay, this is the instruction memory, and then register. So there is I did not, or there's the file here. Okay. Okay, so let's think about the archive instruction like add x1, x2, x3. So it means that this is the add rd, rs1, rs2. And then I already explained that in order to execute this archive instruction, the archive instruction includes 2 source registers and then 1 destination register. So this instruction needs to access register file. Okay, so you can find the read register 1. So this is the rs1, and then this is the read register 2. This is the rs2, and then write register. This is the rd. So what is the function of this register file? So if rs1 is given, then we can read data stored in this rs1. Okay, so what is the read data? So let us assume that this register file has the rf array, okay, data array. So we can just index this rf data array using the rs1. Okay, so this is the rf and rs1. Then read data 2. This is the rf and rs2. Okay, so this is the behavior of register file. And then for the write operation, so in order to write a certain data to the register, then we require the RD and then write data. The write data is the 32-bit data. Okay, so then you can find the control signal here. The control signal, so it's a reg write. So if this control signal is 1, then the register file performs the register write. If the reg write, the register write is a 0, then register file does not update the RD. This is required. Why? Some instructions update registers, right? Like those R-type instructions. But some instructions, such as branch or store, these instructions do not update the register file, the general purpose register file, right? So in this case, we need to avoid the register write. Okay, that's why we need to control the register write here. Okay, so that's why, so this the register includes the reg write. So this is the control signal. So control signal just determines the output, the control of this data path element. Okay, so if the RF1, the RF indexed by RS1 and RF indexed by RS2 is the out from the register file, then it can be given to the ALU. And then we can select the ALU operation, right? Because the ALU also supports the various arithmetic or logic operations. So we need to select. So based on the ALU operation bit, then ALU just uh, determines the required operation. So this, okay, so this is the R-type instruction, and then you can also find the R-type RISC-V R-type instruction format. Okay, so you can find that the RD is included in the instruction, and the RS1 and RS2 is included. So that's why in the previous figure, the instruction is connected to the register 1, register 2, the RS1, RS2, and RD. Okay, but you need to remember that actually the entire instruction data is not connected because this is the 5-bit signal, right? So among these 32-bit data of instruction, this 5-bit RS1 is connected to this port. RS2, another 5-bit, is given to this port. RD 5-bit is connected to the write to register port. Okay, so you can find that instruction includes the RS1, the register numbers, RS2, and RD, and then these field in the instructions are given to the RS1 port, RS2 port, RD port. Okay. So then how can we design a register file in system Verilog? So this is the behavioral model. So as I mentioned, a register file is an array of general purpose registers. And then it's similar to the memory. So memory is the array of data. Okay, so array of data space. So register file is the array of general purpose registers. And then how many registers are in the RISC-V instruction set? How many general purpose registers? 32, right? From x0 to x31, right? So there are 32 general purpose registers, and then the size of a single register file is 32-bit. And then like the memory, so you can find the RF underbar data. So this is the array of register. How many? 0 to 31, right? Because it represents the x0 to x31. Okay. Okay. And then this is the write operation. So I just skip the write operation here. And then read operation. So how can we read data from this register file? So you can find that the register file includes the RF underbar data array, and then this array includes 32 elements, right? Then how can we define the read operation? The read operation, so like the memory, so it's very simple. So you can just read data like the RS1. So this means RS1 is the index for this read data 1. Is this okay? Is this okay? Usually okay. Why? I mentioned normal. So for most cases, it's okay, but it's not okay. Why? X0 is the zero register, which means the output of X0 is always 0. So which means we need to define this behavior. Okay, so actually this is not correct. So if the RS1 is equal to 0, then it's 0, right? It's a 0. Otherwise, it's the RF data indexed by RS1. Okay, so this is a normal case. Okay, and then actually we need to also consider the special case like the x0. So the output of x0 is always 0 regardless the data in x0, right? So because this is the 0 register. And then write operation. So how can we define the write operation? So actually you can find the positive edge of clock here. Okay. So register is actually updated on the rising edge of the clock. Okay. Even though this component does not include the clock port, but actually the clock signal is required. Okay. How can you define the output, the register write, the register write behavior? If the regular write is 1, so I mentioned that if the regular write is 1, then the write is only enabled. Okay. So we need to define this condition. If the regular write is 1, then how? It's simple, right? It's RF data indexed by RD is actually we need to use the non-blocking in the system Verilog is where is the data? This data. So data in So, so this is the data in, okay, the input data, and then this is the RD. So you can find that, oh, on the rising edge of the clock, and then if the regularity is 1, so this is the control signal, then RF data indexed by RD is updated by data in. Okay, so we can design the register file like this. Okay, so ALU, so ALU is a simple, so based on the some ALU control bit, so you can find the so ALU control bit here, and then ALU just generate the output. So you can define the function of the ALU like this. So ALU out is the function of RS1 data and RS2 data. And then this function is defined by ALU control, right? ALU operation. So it means based on this ALU operation, this function can be addition, subtraction, or AND, or exclusive or, and then blah, blah, blah. Okay? We can define the behavior of ALU like this. Okay? And then load store. So load store, for the load store instructions, okay, so you can find the load store instructions. So it's 40, okay. So load word and then store word, and then for the load instruction, you can find that this has the RD and then RS1 and immediate. Okay, immediate actually here. So it performs the immediate plus RS1, and then using this RS address, then it accesses the data memory, right? So this is also the memory, and then the actually we can read this data memory. So this is the load instruction, and then we can write the data to the data memory. So this is for the store instruction. Okay, and then you can find the data import here and then data output here. And then for the load instruction, you can find that. So we need to use the immediate value, right? So immediate value needs to be decoded. So it is immediate value needs to be figured out from the instruction. Okay, so immediate generator here. So load instruction has the I format, I type. So you can find the immediate field here, and then RS1 here, RD is here. Okay. So RD is given to the register file, the RD port here, RD port, and then RS1 can be given to the RS1 port of the register file. Okay. Now how about the immediate? So immediate generation. So actually, uh, so you can find that immediate value can be also given to the another port, the second port of the ALU. So for the second port of the ALU can receive the RS2 data or immediate value, right? Then what is the input? What is the input width of this second port of the ALU? Each 32-bit, right? Because the RS2 data is the 32-bit. So which means from the immediate field, we need to generate the 32-bit immediate data, the 32-bit data. But the I type just includes the 12-bit immediate data. So what is required? bit extension is required. Okay. And then because this immediate data is the two's complement immediate data, so we need to perform sign extension. So this is the some type, the immediate data, immediate generation by instruction type. So in the I type, so like the add I or load word, so we can just extend the sign bit of this 12-bit immediate data. So 12-bit immediate data is here, the instruction 31 down to 20. And then because this 31 is the sign bit, bit number 31 is just repeated. It's a sign extension. For the S type, the immediate field is here and here, but also this is the sign bit. So we can just apply the sign extension. But actually, inst 11 down to 7 is here. The B type, the branch instruction. Branch instruction also has the immediate data. So we can just generate the 32-bit immediate data like this. Okay, so based on some instruction types, we can generate the immediate data differently. Okay. Okay. So I will stop here, and then for the next class. So actually, I need to make a presentation for some other some AI conference at the conference. So we cannot have the in-person lecture for the next class. Okay. So for the next class, I will post the recorded videos and you can watch the recorded video. But just remember that we do not have in-person lecture for the next class. Okay. Okay. Thank you for your attention. Okay.